I just want to tell you a couple more things about continuous functions that are going to help us as we're going along. So we've seen that all polynomials are continuous. We've seen that all rational functions are continuous. I've told you that the trig functions are continuous, even though I didn't show it or show you the proof. And there's another way that we like to build up new continuous functions from old ones. And the way I'll explain this is, so first of all, if you take any two continuous functions at all, then their sum is going to be a continuous function. So for instance, if you have, say, f of x equals x, you have g of x equals, I don't know, sine of x. You add them together, x plus sine of x. Is that continuous or not? The answer is yes. And the reason, again, comes to us from those limit laws, because if you want to take the limit as x goes to whatever point you like, let's pick pi over 2. You want to test whether this is continuous at pi over 2. And so what you do is you take the limit of the sum and you ask yourself, is this going to be pi over 2 plus sine of pi over 2? And yeah, the answer is completely yes. And the reason for that is because that sum limit law tells you that limit is going to be equal to the limit of f of x plus the limit of g of x. So whenever you take the sum of two functions and then take their limit, you can split that up as the sum of two limits. And that will then tell you that, okay, because these two functions are continuous, the definition of continuous is that you can take that limit by plugging in the number. So this is all going to be equal to f of pi over 2 plus g of pi over 2. It's going to be equal to pi over 2 plus 1, sine pi over 2 being equal to 1. So the sum of two continuous functions is continuous. The same argument with the limit law for quotients tells you that the quotient of two continuous functions is continuous provided that the denominator is not equal to 0. We've already seen an example of that. You can look at sine of x over x. That's the quotient of two continuous functions, isn't it? This is going to be continuous so long as x is not equal to 0. We saw that in a previous video. It's discontinuous at x equals 0, and that discontinuity is removable. So similarly for the other ones, the product of two continuous functions is continuous. And if you take a continuous function and multiply it by a constant, that's going to stay continuous. So now we have a nice full sandbox of lots and lots of different functions that we know are continuous that we can work with. There's one other thing about continuous functions that I'll show you, and that has to do with inverses. So say that you have a function f of x, and I don't know what its domain is. Its domain could be anything, like an interval from a to b. We usually notate that by the domain and range of a function by f and then a colon, and then you put the domain here like an interval. And you'll put a little arrow, and I could use, this font is called Blackboard Bold. It notates the entire real line from negative infinity to positive infinity. So say that you've got a function whose domain is some interval, and say that the inverse function exists. Inverse functions don't always have to exist, so f of x equals x squared. There's no inverse because of what we call the horizontal line test. You'll have one y value associated to multiple x values, so the inverse can't exist. But if it does, if you've got a function with the inverse exists, and with f being continuous. You put that together, and what you can conclude from that is that the inverse function is continuous on its domain. So in other words, if you have a function, if that function has an inverse function, then that inverse will automatically be continuous. This is actually a pretty hard theorem. It goes by the name invariance of domain, if you want to Google it. It's a special case of that. It was not discovered, if I recall correctly, until about 1912 by a mathematician named Brouwer, who was studying a very different field called topology, but that also has to do with continuous functions. So if you go further on in mathematics, take some further courses, then I could show you the proof of that. But for now, I'm just telling you the information that in most cases, if that inverse function exists, then it's probably going to be continuous too. Okay.